Welcome to this lecture on the standard atmosphere. The last time we discussed ballooning and derived the equation of state, but today we're going to add an extra dimension. We're going to go vertical. We're going to see what happens to those parameters if you go really high in the atmosphere. Somebody who actually went really to a high altitude in the atmosphere was Felix Baumgartner. He made a record jump of over 38 kilometers altitude using a helium balloon to get to this altitude. And you can see him here wearing a sort of astronaut suit. But in a way, he was merely repeating what was already done in 1960 by Joe Kittinger. He jumped from over 31 kilometers, and he did it to investigate the effects of high altitude ejection from planes like the SR-71 Blackbird, for instance. You see that they both are wearing sort of space suits. Well, this brings up the question, of course, how close are you to space in the atmosphere at these altitudes? Is it just like on sea level but with slightly thinner air? Or is it really approaching the limits of the atmosphere, and is it really a space-like environment? With today's equations, you can calculate this yourself, and for one of the two we will also do this in the course. What is the standard atmosphere? The standard atmosphere is merely a reference atmosphere that we use for different purposes. There are three main reasons to use a standard atmosphere. The first one is to have a reference to discuss the performance specifications of an aircraft. What does it mean if I say the aircraft can fly up to 20,000 feet? What was the weather like in those days? This varies. The maximum altitude depends on the weather and the actual temperature density of the specific day of the specific location. Of course, to be able to compare different aircraft specifications, we need one reference. But even further, to measure the altitude, we often measure the pressure, for instance, and we need a standard agreement on how to translate these measurements into the actual altitude and speed parameters. So the definition of altitudes and densities is also something for which we use a reference atmosphere. Even if we're wrong on our altitude, if we're both wrong in the same way, we can still make certain that we miss each other at different altitudes. And the third one is the one that we use it for specifically, is as a model for our calculations, for simulations and analysis. Our standard atmosphere is still a model atmosphere. What does this model comprise? The standard atmosphere is a definition of the three parameters which we had in the equation of state: the pressure, the air density and the temperature, but then given as a function of altitude. We cannot freely choose these parameters. We have some limitations. We want to make sure that our model atmosphere, our reference atmosphere, is physically correct. So it needs to obey the previously derived equation of state, our gas law, so to speak. So P is rho times R times T as a law which we have to use. We still need to need more laws to really define this, and therefore we also need to derive how our pressure will increase due to the gravity when you get higher. You see on the right side of the slide, you see the column of air indicated with a pressure at sea level. Over 100,000 Newton per square meter. This is the standard sea pressure level which we use. But think about this number. This is, if we transfer to kilograms per square meter, this means that for every square meter there is a weight of 10,000 kilograms pushing on it, which is huge. On the other hand, if you think about a cubic meter, this weighs about a little over 1 kilogram. This would also mean that 10,000 of those blocks, so 10 kilometers altitude, would be sufficient to generate this amount of pressure. And obviously, the atmosphere is much higher than 10 kilometers, which is in the slide indicated by the paler blue when you get higher in the column. This means also that all the parameters, the density, the pressure, the temperature, they all vary if you go up, and it all has to obey physics. But let's use this last assumption that the pressure increase is merely the result of the weight of the air on top of it. Let's use this to find our second physical law to which our model atmosphere needs to obey. I say model atmosphere because we have to keep in mind that we are ignoring several things. First of all, we are ignoring the weather. This means both the convection, vertical winds, as well as the water, vapor and gas form, which is present in the atmosphere, is ignored in our model atmosphere. We are sort of looking at the atmosphere on the right side here, which has a blue sky, clear sky, and is completely in equilibrium. And this is also something we will use in our advantage to make our calculations. So let's look at how pressure is a result of gravity. For this, we are going to derive an equation which is known as the hydrostatic equation. When we're talking about air, you could say it's the aerostatic equation, but the principle is the same. Hydrostatic or aerostatic indicates the medium, and static means there's equilibrium in our atmosphere. We see here a small disk of air. Which forces are acting upon this small disk of air? Well, first of all, let's define the size of the disk. We take it for a limited altitude, which we call delta H, and we call the top surface, which is colored gray here, we call it the area A. Well, the first force which acts upon any volume of air is, of course, the gravity, which is the mass times the gravity acceleration, the gravity constant. This force is somehow countered by the pressure forces, and there are two of them in the vertical direction. There's one on the bottom side of the disk, which we call P, and slightly higher there is a pressure P plus delta P acting on the top surface of this disk. Well, this is our model, our small disk of air, which we will look at to later derive it for the large cylinder which we saw in the previous slides. So, I said it is in equilibrium. What does it mean? If the disk of air stays in the same position, this basically means that the forces in the downward direction need to be equal to the sum of the forces in the upward direction. Well, let's look what the forces are. First, the forces downward. First of all, we have the gravity. Second, we have one of the pressure forces, P plus delta P, also acting downwards. And to make this into a force, we need to multiply it by the area of the top surface, which we call A. These are the forces acting in a downward direction. Which forces are working in the upward direction? Well, that's only one force, P times the area of the bottom surface, which is the same as the area on the top surface. So this is our start, this is our equation, the equilibrium of forces down and up. Well, let's look a bit closer at what these different forces are. Mass times G. Well, we know what the mass is. The mass is basically the density times the volume. So we can replace m by the density times the area times the altitude of the disk. The area times the altitude of the disk is the volume of the disk. Multiply this by g, and we have a different expression for the force of gravity. Let's also make sure that we have all the pressure forces on one side of the equation, and let's move them to the right side of the equation. This means P to A remains on the same side, but the other part is added to it with a minus sign because we have moved it to the right side of the equation. And here we can see that we can already start to simplify our equation. First of all, we can see that P times A minus P times A reduces and disappears into zero. And we can also see that if we have A on both sides of the equation, we can divide by the area A, which means that we have a much simpler equation, which is rho times the altitude of the disk times gravity is equal to minus the pressure change. If I invert this equation, change the direction from left to right, I get basically the start of our hydrostatic equation. The change in pressure over this altitude disk is equal to minus the air density times gravity times the altitude of the disk. Well, we have made some simplifications here. For instance, we have used the density as if it is a constant density throughout the disk, while in reality we have said that the density will vary with the altitude. And this means that what we've done so far is only true for very small altitudes, for very thin disks, for very small delta H. In general, we write those equations then not with the delta sign, but with the D, which means our total hydrostatic equation looks like this. dP equals minus rho times G times the H. And this is basically the change in pressure at any altitude is a result of the gravity, the thing we started with, but now explained in the formula. So we have two laws which we should use, to which our model atmosphere should obey these laws. That's the equation of state and our hydrostatic equation. Those are two equations. We see on the top side of the slide here that we need three parameters. Well, we still have some problems then, because first of all, three parameters and two equations means we still have one unknown variable. And the other problem that we have is that basically one of the equations only describes a change in pressure as a result of a change in altitude. So what do we need to do to fix this? We need to define one variable, for instance the temperature, as a function of altitude, to be able to calculate the others. Also, we need to define a start value, because one of the formulas only talks about change. Well, we choose the temperature. We could have chosen any other, but we choose the temperature. And this gives us also some freedom to model our atmosphere. We can choose which atmosphere we model, where on Earth. And we have chosen in the standard atmosphere for sort of moderate latitude, and have used that as our model atmosphere, our average atmosphere. Let's have a look at the definition for temperature. Here we see on the right side of the slide, we see a red line indicating the temperature on the x-axis as a function of the altitude on the y-axis. And it looks a bit strange, perhaps, if you look at it first sight. But this is, believe me, this is really modeled at a real atmosphere. It's very close to the actual average of the atmosphere. In fact, if we look at the first value at sea level, the pressure, which is 101,325 Pascal, so Newton per square meter, this value you could use with the surface area of the Earth to make an estimate of the mass of the atmosphere, and you will be correct in only 2% of the total mass of the Earth you might miss. So apart from a model atmosphere at a moderate latitude, it's also a very good average for the Earth as a whole. You can see that the temperature we've chosen is also from moderate latitudes, 15 degrees Celsius, which equals to 288.15 Kelvin. And of course, in our equations, we will use Kelvin. With the equation of state, you can then calculate the air density, which is 1.225 kilogram per meter cubed. So this is slightly over 1 kilogram per cubic meter. That's the start value. We use those values at sea level. But now we have the freedom to choose the temperature, and the red line indicates this change in temperature. And maybe you've once heard a child ask, why doesn't it get warmer when you get higher in the air? Because you get closer to the sun. And then we always say, no, it's not like that, because you have the sun rays go through the atmosphere, heat the Earth, and due to both the radiation of the Earth and the contact of the Earth, the atmosphere is heated from the downside and not from the side of the sun. Well, if you look closely at this figure, you can see that if you go really high in the atmosphere, there is in fact a part where the temperature increases when you get closer to the sun. And that's the highest part of the atmosphere, that's the thermosphere. But let's start at sea level, where we have our start values. There indeed, as we know from experience, if you are in the mountains, if you get higher, it gets colder. There's snow on the top of the mountains. And this is the value with the temperature decreases is about minus 6.5 degrees per kilometer. This is true for Kelvin and Celsius, as they have the same step in degrees. So minus 6.5 Kelvin per kilometer. So on a mountain of 2,000 meters, there's 13 degrees colder than in the valley at sea level. This goes on until around 11 kilometers. And then we see that in our model atmosphere, you see a sudden turn in temperature. In reality, this might be a more gradient. But here we have an area where the temperature is rather constant, and this is called the stratosphere, the start of the stratosphere. And then later on, the temperature even increases, and it gets colder again, and it increases again. Why does this happen? Because, like I said, this is close to reality. Well, I already said that in the thermosphere, the temperature increases due to the radiation of the sun. But why does it increase around the middle of the figure, the stratopause, and then decrease again and increase again? Remember that for heat you need energy. And around the 50 kilometers altitude, there's a lot of ozone. And even though the heat radiation is already absorbed in the thermosphere, the ultraviolet radiation is absorbed by the ozone layer. And when a radiation is absorbed, it needs to go somewhere, and as always in physics, if you lose track of energy, it becomes heat. And here it's the same, and that's why at the altitude of the ozone layer, the temperature is actually higher than the altitudes above and below. Then it gets colder again, and in the stratosphere it's really cold, minus 55 degrees in that range. And then it becomes warmer again when you get closer to the Earth, like I said, due to the contact with the Earth and the radiation of the Earth. So this is our model atmosphere, and we use this as an example for the start of our equations. But we only now have the temperature, and we still need the pressure and the density. Let's see how we do that. The definition of the temperature for altitudes and the gradient for the different layers is also given in this table. We see for all the layers a so-called lapse rate, which indicate the degrees Celsius per kilometer or Kelvin per kilometer, with which the temperature decreases or increases. And we see indeed different values, negative, positive, and even 0. Together with the start values of the first row, this is all we need to define our standard atmosphere. With the gradient and the base temperature, we can very quickly calculate the temperature at all the the borders of the different layers. But how do we calculate the pressure and the density? Of course, if we have one of the two, we can very quickly calculate the other with the equation of state. Well, we have two equations. We have the equation of state and the hydrostatic. Let's start with the bottom one, the change in pressure, because we're looking for the pressure. So dP equals minus rho times G times dH. Let's use that as a start for the derivation of the standard atmosphere. With our table, which gives the temperature for the altitude and the start values, together with the two equations that we have derived, we have everything we need to make the complete derivation for the missing parameters, the pressure and the density, for the standard atmosphere. And this is what we will do in the next video clip.